Okay, let's continue. So, in the previous video, we introduced one specific type of continuous random variables. It's uniform distribution. Okay, but of course, we may have some random variables that's not uniform. So let's consider our classroom temperature again. So let X be the temperature of our classroom when the next lecture starts. If we make this definition, and I think it's safe to say that X is within 0 to 50, right? So it should be fine. But we know that X would not be uniform within 0 and 50 because it's more likely for X to be within 20 to 30. Okay, that's a more reasonable range for the classroom temperature. It's less likely for X to be within 10 to 20 or 30 to 40. It's even more impossible for X to be within 0 to 10 or 40 to 50. So within the range of possible values, some subsets may be more likely for X to occur and some are not. So that means the likelihood of X in different intervals can be different. Or say it more intuitively. With higher probability, we will see X to be close to 25, and with smaller probability for X to be close to 0 or 50. That should be reasonable. So we need to have a way to measure or to represent that kind of different likelihood. Okay? Technically, we need to introduce the following concept to you. We use something called a probability density function, okay, abbreviated as PDF, to describe the likelihood of all those possible values. So we use this notation f of x to do the description. F of x is a function of x, and x are all the possible values of your random variable. Then larger f of x would mean a higher likelihood. So you're going to see that the value of f of x does not mean physically anything. However, the relative height of f of x can tell you something. When you have a random variable, you have its PDF, and when f of x is higher here, then the probability for you to see x to locate here would be higher. Specifically, let's see an example for this x. Okay, x is our classroom temperature. Let's assume that its PDF is here. Okay, and the depiction is here. So we say that with the highest probability, x would be between 20 and 30. Okay, between 20 and 30. And here we say its value is 0.05. Let's ignore the question about why it is 0.05. Let's ignore it for a while. But you can see that this number is the highest, just like this height is the highest. Okay, within 20 and 30. And according to our description here, that means x would be within 20 to 30 with the highest probability. The second possibility, I should say the second situation is for x to be within 10 to 20 or within 30 to 40. Here the PDF is 0.02. Okay, here. And it's lower. That means x would be within 10 to 20 or 30 to 40 with a lower probability. And for less than 10 or greater than 40, it's even lower. Okay, so with this graph or this functional form, we express or we describe the random variable x to have the following property. Here we have the highest probability. Here and here has the lower one, and here has the least one. Given the PDF, the probability for x to be smaller than any given value would be calculated in this way. Okay, what's this? The probability for the random variable x to be smaller than a given value small x can be calculated as an integral from 0 to x. Okay, integration with respect to x of the PDF. Here, just to remind you, capital X is our random variable, so you don't know what's its value. So that's why when you talk about it, we talk about some kind of probability. But a small x is a given number. So given x, you ask, what's the probability for your capital X to be smaller than that? Well, you don't really need to know calculus in this course, but you need to know its idea. Its idea is the area below the PDF. The area below the PDF from 0 to x. When you know this, then it makes sense to you that you prefer higher PDF, or you prefer f of x to be larger, so that the probability for x to be within that region gets higher. Intuitively, when we do this integration, we are taking the sum of all the likelihood of all the values between 0 to x. That accumulation gives us the probability. Now, you can intuitively think f of x measures the likelihood for capital X to be the small x. Okay? You can say that f of x equals the likelihood for capital X to be small x. Here we use the term likelihood instead of probability because you know the probability for x to be a given number would be 0. So we tend to avoid that term. Once you accumulate all the likelihood for all the values within a given range, it becomes your probability. Okay, that's just concepts. If you just want to do calculation, let's do it here. For example, given that random variable capital X, I can calculate its probability for x to be less than 30 by finding all the area below the PDF. So 30 is here. From 0 to 30, I want to calculate the area below my PDF. Okay, the area below my PDF. So we have 3 parts. From 0 to 10 is a rectangle. The width is 10. Okay, and the height is 0.005. For 10 to 20 is another rectangle. Okay, the area is here. From 20 to 30 is another rectangle. Okay, it's here. So once we do all these calculations, we can sum them up. The probability for x to be less than 30 is exactly 0.75. So now, first, a probability for x to be within a region can be calculated according to the area below the PDF. Okay, so that's the first thing. The second thing is the value of your PDF measures the likelihood of x. Okay, that's the second thing. And finally, you now can understand why we have some specific numbers for f of x. Y is 0.05, 0.005, y is 0.02, y is 0.05. Because we need to make sure that the area below the curve can really measure something, can really measure the probability. Very quickly, as another example, the probability for x to be less than or equal to 18, again, is the area below the curve, or below the PDF, from 0 to 18. So again, we have two rectangles. The first one is still 10 times 0.005, and the second is now the width is only 8, and the height is still 0.02. So we sum them up, we get 0.21. That's the probability for x to be less than 18. Now we can have one observation. The probability for x to be less than 18 is just 21%, right? But the probability for x to be less than 30 is actually 75%. And we can see they are not proportional. 18 and 30, the ratio is 18 over 30, right? But the probability is not of that ratio. 0.21 is less than 18 over 30 times 75%. Okay, 75%. So that means because our probability distribution is not uniform, x would be more likely to occur here than there. So given two numbers, when we want to calculate the probability for x to be below that two numbers, those probabilities would not be proportional to those two numbers. Okay? Or more concretely, this is because x is more likely to be within 20 to 30. Okay? So when you are talking about from 0 to 30, this part would give you a high probability. Okay? In fact, you may want to calculate the probability for x to be within 20 to 30 is 50%. It's 50%. So that's why the probability between 0 to 18 is small, but the probability between 0 to 30 is much higher. Because this probability would be very useful and we need to calculate it very often, we give it a special name. So given any value small x, we define this probability as the cumulative distribution function. Okay, the cumulative distribution function of x. Okay, so given small x, we define this probability. For any x, we have that probability. So the function of that probability is called CDF. Okay, it's just the cumulative probability up to the given value x. Okay, so you have small x and you have capital X. Technically, small f, you do an integration, you get capital F. But that integral is not very important to you. What's important is that you are actually talking about the area starting from the lowest bound to a given value x. That area is the probability you need. Okay, so this is just a repeat of that previous sentence. And given any region A to B, now we can do the calculation in this way. If I am interested in about a probability from A to B, then I can simply do the calculation by first finding the probability below B and then subtract that with the probability for x to be less than A. Okay? This would be larger than that because B is greater than A. So I just need to do two calculations for my CDF. I just need to plug in B and plug in A into my CDF and do a subtraction. That's going to be my answer. Just like here. If I want to calculate the probability for x to be within 18 to 30, then I just need to do two plugging-ins and do one subtraction. I'm going to get 54%. That's my probability for x to be within 18 to 30. So, a very quick review and summary. Continuous random variables, they are important in inferential statistics, right? Because many statistics many quantities that we calculate from the random sample would be continuous random variables. Okay, just like the example x bar we mentioned to you. So because of that, we need to have a way to describe, to measure continuous random variables. And when we want to infer a parameter, for example, when you want to use x bar to do some guess to your mu, we rely on what? Rely on the probability distribution of a statistics. You don't know who will be in your sample, so you don't know. You cannot 100% predict what will be your sample mean x bar. So you need to have you know that x bar would be somewhat random, and you need to know its distribution so that you can measure mu. Okay, that's the central heart of inferential statistics. Okay, we're going to talk about that more in the future. The concepts of density and distribution functions, that just means PDF and CDF, that's very important. A PDF describes the likelihood of a given value, and then the CDF is the probability for you to see whether X would be within this region or that region. Okay, PDF describes likelihood, not probability, and the CDF is used to calculate the probability for X to be within a given region. In most cases, we will just use software to calculate the probability. Okay, the software gives you some functions so that as long as you know which region you want, you're going to get that area under the curve directly by invoking the function. Okay, so you don't need to worry about calculation. You don't need to do integration. You don't need to calculate area of rectangles. All you need to know is to know what to calculate. Within which region you want X to be occur. That's what you need. Okay, let's stop here and take a rest. Thank you.